Hello and welcome back to my YouTube channel or the Big Structure Hub. This is the #1 channel for structural insight, and it is a place where you learn, build, and innovate. So today I want to tackle example number 2, and the question is on the board, and this is the design of steel to BS 5950. So the question reads, a proposed cantilever beam 1 meter long is to be built into a concrete wall as shown below. It supports a characteristics dead and imposed load of 450 kilonewton per meter and 270 kilonewton per meter, respectively. Select a suitable universal beam section in S275 steel to satisfy bending, shear, and deflection criteria only. So this is the cantilever beam. As you can see, it is carrying 450 kilonewton per meter. This is the GK, which is dead load, and 270 kilonewton per meter QK, and it is spanning 1 meter. So a cantilever beam is a beam which is permanently fixed on one side and hanging on the other sides, as you can see. So it is permanently fixed at A and it is hanging on this side. So let's see how you can tackle such a question. And before I begin solving this question, I want to capture the most important information on this column so that I can rub here and create space for our calculation. So I will draw the beam. So the strength is S275, like that. So let me rub here so that we can continue with our calculation. So solution. So this is our beam, our cantilever beam. So the loading is 450 kilonewton per meter. This is GK, and 270 kilonewton per meter. This is QK, and the beam is 1 meter long. So the first thing to do is to calculate the total ultimate load applied on this beam so that we can be able to calculate the reaction at A. So let's start. So the total ultimate load is equal to 1.4 GK plus 1.6 QK. So this one is equal to 1.4 times GK is 450 plus 1.6 times 270. So this one is equal to 1062. Remember the SI unit is kilonewton per meter. So after getting this total ultimate load, now you can calculate the reaction. So reaction at A, which is equal to FV, is equal to WL, yes, W times L. So this one is equal to W is 1062 kilonewton per meter times L. L is 1 meter. So this will cancel with this. So we have 1062 kilonewton. So you can come here and say if V is equal to 1062. Remember, this is not a simply supported beam, whereby to calculate the reaction, we always use this formula WL over 2 for a UDL. But for a point load, is W, for a point load with a concentric load, is W over 2. But for this case, this is a cantilever beam. So this is the reaction at A, which is FV. After this, you can now calculate our moment. So let's now calculate the moment. So if this is the beam, and this is the loading, this is 1062 kilonewton per meter, this one, and from here to here is 1 meter. Then it means the maximum or the design moment, so design moment is equal to WL square over 2, because the design moment will be the maximum moment at support A. So this is support A, and you know the basic formula for moment is force times perpendicular distance. So if we have to determine the bending moment or the maximum bending moment at this point, it will be force times perpendicular distance. So because this is in UDL, you'll change first to a point load. So a point load, you will take this UDL, which is W times L. By doing so, you have changed it from UDL to a point load. Then for a bending moment, a UDL, for a bending moment, it acts at the center of this span. So you'll take WL times again L over 2. If you simplify this formula, you'll get WL square over 2. Here it is. So let's now find the value for design moment. So this one is equal to 1062 times 1 square all over 2. So this one is equal to 531 kilonewton meter. Again, we'll come here and say M is equal to 531 kilonewton meter. We now proceed to initial selection. Initial selection. So for initial selection, you need the plastic modulus, which is Sx, and it should be greater than M over Py. So M is the the design moment, and Py is 275. So this one is equal to, so Sx, which is the plastic modulus, must be greater than M which is 531 times 10 raised power 6. We change it from kilonewton meter to Newton millimeter. So you will multiply by 10 raised power 6 over Py, which is 275. So this one is equal to, 1931, no, 1.931 times 10 raised power 6. Remember, it is in millimeter cubic. So, but SS, which is the plastic modulus in the table, is given in centimeter cubic. So you will multiply by 10 raised power negative 3 to convert it from millimeter cubic to centimeter cubic. So this one is equal to 1931 centimeter cubic. So this is Sx, like that. So after getting this, we will now proceed to the table and obtain or select the section based on this plastic modulus. So I will show you. So as you can see, this is the table where we obtain the section properties. So as you can see, we have the size, serial size. Just follow my cursor. We have the serial size. We have the mass per meter, section, and so on. So already we have calculated our plastic modulus. So we'll go where the plastic modulus is, as you can see, and we will go for axis XX. You can see it is in centimeter cubic. So, and we have calculated the plastic modulus, and we have the value as 1931. So we want to pick a value which is slightly higher than that. So we will come here and check for a value that is slightly higher than 1931. So along the x axis, slightly higher than that. So as you can see, we have 2060. See where the cursor is. So that is 2060. So in line with that 2060, you will proceed and pick the properties for that. So you will come here and begin with the section size. So as you can see, the section size is 533 depth times 210 width times 82 kilogram per meter. Then 528.3, just follow my cursor, that is D. We have B 208.7. We have T, you pick that value in line with the plastic modulus, which is 2060, and we will pick all other properties as you write their values, because they will help you in our proceeding calculation. So that is how you read that table. So you will now say select, as you have seen from the table, or try. You will say try, because you are not sure if it will fail or not. So try 533 times 210 times 82 universal beam. And then the plastic modulus from the table is 2060 centimeter cubic, like that. So this is the depth, the width, and kilogram per meter, like that. And then we will come to section properties. Again, this is from the table. You have seen it, section properties. You just pick the section properties in line with the plastic modulus, which is 2060. So D is equal to 5, 28.3 millimeter. You have seen this. B is equal to 208.7 millimeter. And then small t is equal to 9.6 millimeter. Capital T is equal to 13.2 millimeter. We have the R is equal to 12.7 millimeter. And then D is equal to 476.5 millimeter. B over T, so this is for flange, is equal to 7.91. And then for the web, which is D over T, small t, is equal to 49.6, like that. IXX is equal to 47,500 centimeter to power of 4. We have that XX is equal to 1800 centimeter to power of 3, like that. Now we proceed to strength classification. We want now to classify the strength of this section. So these section properties, we will use them in our proceeding calculation. So strength classification. So for you to classify the section based on its strength, you need these parameters. You need this table. I hope you have this table. So this is T and this is PY. So here we have less than 16 millimeter. This is 275. We have less than 40 millimeter. And for your information, in your exam, don't write this table. Just classify based on this capital T you have obtained from the universal beam table. I'm just doing it for the learning purposes, but for exam, don't waste time writing this table. This is 265. We have less than 100. No, less than 63. So this is 255. And the last one, less than 100. So this is 245. So our T here is 13.2. We can write this here. So D is equal to 528. B is equal to 208.7. T is equal to 9.6. Capital T is equal to 13.2. D over T is equal to 49.6. D is equal to 476.5. B over T is equal to 7.91. And then D over T is equal to 49.6. IXX is equal to 47,500 centimeter to power of 4. ZXX is equal to 1800 centimeter cubed. So we will classify this based on the strength, no, based on the thickness of the flange, so which is 13.2 millimeter. As you can see, 13.2 millimeter is below this one. So you can say therefore 13.2 millimeter is less than 16 millimeter. Therefore, the Py is equal to 275 Newton per millimeter square. So this is the strength of this section. We now proceed to section classification. You are now to classify the web, whether it is a plastic, a compact, or a semi-compact. Also for the web. So section classification. Again, for section classification, for you to classify whether a web or the flange is plastic, compact, or semi-compact, you also need this table. In your exam, don't draw this table. You have the limiting proportion. You have the plastic. You have the compact and the semi-compact. So you have B over T, and we have D over T. So this is 9.0, like that, like that. Don't draw this in your exam. So we have, this is given by 275 over Py. So for our case, it will be 275 over 275, which is equal to 1. So let's now start with the flange. So B over capital T is for the flange. We want now to classify this flange, whether it is plastic, compact, or semi-compact. So we have been given this ratio to be B over T. This should be capital T. To be 7.91. And for plastic, it must be less 9.0, like that. So 7.91 is less 9 times 1. Therefore, the flange is plastic, is class 1 plastic, is class 1 plastic. We proceed to to the web. So the web, we will use d over small t. So this one is for the web. So d over small t is equal to 49.6, and it must be less, as you can see here, it falls here, it must be less 80, like that. So where 80 times 1 remain 80. Also, therefore web is class 1 plastic. Both of them are a class 1 plastic, like that. So we have classified the flange as class 1 plastic and also the web as class 1 plastic. So you will say the section which is 533 by 210 by 82 kilogram per meter is class 1 plastic. So you have now classified the section. We now proceed to shear strength. So for shear strength, we know that if d over t is less than 70, is less than this, then there is no need for shear buckling to be considered. So let's see, our d over t is 49.6 is less than 70 times 1. So therefore, no shear buckling will not be considered, like that. We now proceed to the strength capacity, the shear capacity. Before we proceed to shear capacity, we know that our shear force, which is FV is equal to 1062 kilonewton, and the shear capacity, which is PV, is given by this formula 0.6 py dt. So this one, which imply PV, so this one is equal to 0.6 times 275 times d here is 528. I think it's 528 point something. Let me check. Yes, 528.3. So 528.3 times small t, which is 9.6. And of course, we'll multiply by 10 to power of -3 to change it from Newton to kilonewton. So this one is equal to 837 kilonewton. So Remember, the code says that the FV must be less than PV for the section to be okay in shear. But for this case, you can see that FV, which is 1062, is greater than PV, which is 837. Therefore, you will say not okay. Not okay. That's why from the initial selection, I told you we try this section because it can fail. So not okay. So what will you do if this is not okay? You will say that in this case, because the length of the cantilever is so short, the selection of the section will be determined from the shear strength, which is more critical than bending. So try new section. You will say try new section, like that. So you'll again go back to the universal beam table and try new section. I will show you. So as an engineer, you should design a section that will not fail either by bending or shear. So because this one you have selected, the section you have selected will fail by shear, we now try a new section. So you will go back again to the universal beam table and select a plastic modulus which has a higher value than 2060, as the one you selected before. But I will not show you how to select this one from the table because you already know it. I have shown you how to read the table. So you'll say try a new section with a plastic modulus higher than 2060 centimeter cubic. So this is what I have selected. So 610 by 229 by 113 universal beam, and the SX is equal to 3290 centimeter cubic. So as you can see, this value is higher than this. So go back to the table. I hope you have the table and see how I have selected this section. Again, after selecting this section, you will also write the properties of this section because it will help you in calculating. It will help you in our proceeding calculation. Then we will come here and say properties. So we have D is equal to 607.3 millimeter. Let me write it here. I will grab this one because they are irrelevant. So D is equal to 607.3 millimeter. B is equal to 228.2 millimeter. T is equal to 11.2 millimeter. T is equal to 17.3 millimeter. R is equal to 12.7. Small d is equal to 547.3 millimeter. B over T, this is capital T, is equal to 6.60. D over small t is equal to 48.9. Then we have IXX. IX is equal to 87,400 centimeter cubic. We have ZX is equal to 2880 centimeter cubic. And then of course we have the plastic modulus is equal to 3290 centimeter cubic. So having obtained these properties from the table of plastic modulus 3290, we can now continue with our calculation. Again, we'll come here and classify the strengths of this section. So strength classification. So strength classification. So I'm sure you know how to classify the strength of the section. I've already shown you. So we always use capital T. Capital T is the thickness of the flange. If we have a section like this, so this is T, and this is the flange, and this is the web. This is the web, and this is the small d, and this is the capital D, and this is T. So T is equal to 17.3 millimeter. So 17.3 millimeter is greater than 16 millimeter. So you can say 16 millimeter, 17.3 millimeter is greater than 16 millimeter, but less than 40 millimeter. So this is from this table T and PY. So this is 16. We have 16, which correspond to 275. We have 40, which correspond to 265, and so on. So as you can see, this 17 is greater than this, but it is less than this 40. So it means the strength class is 265. So you'll say, therefore, the strength class is equal to 265 Newton per millimeter square. We have already classified the strength class. We can also classify the section. So the section classification. For the web, or let's begin with the flange. For the flange, we will use B over T, which is equal to 6.60. So 6.60 is less than 9.0, whereby this is given by this formula, 275 over Py. So this one is equal to 275 over 265. So this is 1.02. This is 1.02. So it therefore means flange, which is B over T, is equal to 6.60, is less than 9.0 times 1.20. Therefore, the flange is plastic, class 1 plastic. I think I'm just repeating for what I've just done before, but here is for a new selection. I'm doing it for the new selection because our first selection failed. So I won't be going deeper into this because it is just a reflection of what I have done. So flange is plastic. We go for the web. So web, we will use this d over small t, which is equal to 48.9. So this one is less from the table, 80. And this is 80 times 1.02 times 1.02. Therefore, also the web is plastic. We now proceed to the shear strength. So remember, for the first section, it failed. So let's see if the second section will fail or it will pass. So we have the FV, which is equal to 1062 kilonewton, and FV must be less than PV. So PV is equal to 0.6 Py dt. So this one is equal to 0.6. Remember, the strength of our second section is 265 times D. D here is 6 or 7.3, then times T, 11.2. Of course, we'll multiply by 10 raised power negative 3 to get your answer in kilonewton. So let's see if it will fail or not. So this one is equal to 1081 kilonewton. Therefore, as you can see, FV is less than. So FV is less than PV. Therefore, okay. Let's now check if it is a low shear load or a high shear load. So check if it is a high shear load or low shear load. For a low shear load, FV must be less than 0.6 PV. So FV is 1062, and no, let's calculate the 0.6 PV. This is for a low shear load. And for a high shear load, it will be 0.6 PV is less than FV, and FV is less than PV. So this is for a high. So the determinant factor here is 0.6 PV. So 0.6 PV is equal to 0.6 times PV is 1081. 1081, which is equal to 0.6 times 1081 is equal to 648. Therefore, it is a high shear load. As you can see, 648.6 is less than FV, which is 1062, and 1062 is less than PV, which is 1081 kilonewton. We now proceed to moment capacity. So moment capacity for a high shear load is given by the following formula, which is MC is equal to this formula, whereby this is the strength and S is the plastic modulus, and this one is equal to 2 FV over PV minus 1. Then square. And then SV is equal to T D square over 4. So let's begin with this one. So this is 2. FV is 1062 over PV is 1081 minus 1 square. You will get 0.93. And this one, small t is 17. No, small t is 11.2. Then capital D is 607.3 square over 4. So this one is equal to 1.03 times 10 to the power of 6. So MC is equal to PY is 265. S is 3290 because it is in centimeter cubic. So you'll change it to millimeter cubic by multiplying 10 to the power of 3. Then minus this is 0.93 times 1.03 times 10 raised to the power 6. Then times 10 to the power of negative 6, because we want our answer in kilonewton meter. So this one is equal to 618 kilonewton meter. And remember, the moment capacity must be less than or equal to 1.2 PYZ. So P 1.2 times PY is 265. Then Z is this one, 2880. You multiply by 10 to the power of negative 3 to change it from centimeter cubic to millimeter cubic. So this one is equal to it's equal to 915.8 kilonewton meter. So therefore 618 MC is equal to 618, which is less than 915.8. Therefore K. After that, we now proceed to moment due to on weight. So moment due to on weight. Remember our section we selected, it was 610 times 229 times 113 kilogram per meter. So we want to use this mass. So mass is equal to 113 kilogram per meter. We convert it to Newton per millimeter, then to kilonewton per, from Newton per meter to kilonewton per meter. So you take 113 times gravitational acceleration, which is 9.81. Then by doing so, our answer will be in Newton meter. Then we will multiply by 10 raised to the power negative 3 to obtain our answer in kilonewton per meter. So this one is equal to 1.109 kilonewton meter. Kilonewton per meter, not kilonewton meter. And therefore, this is the GK. So we will have to factor in 1.4 times 1.109. So this one will give us 1.6 kilonewton per meter. So it means if this is our cantilever beam and this is the loading of the on weight, which is 1.6 kilonewton per meter, therefore maximum moment at A, or the design moment or a moment due to on weight, is equal to WL square over 2. So WL square over 2 is equal to 1.6 times 1 square. So this is 1 meter over 2. So this is equal to 0.8 kilonewton meter. So applied moment will be the total moment, and the total moment will be 531 plus 0.8. So this one is equal to 531.8 kilonewton meter. Therefore, the applied moment is less than moment capacity, which is 618. Therefore, okay. And we will finalize by deflection. So I want to do now the deflection. So deflection. So the permissible deflection for a cantilever is given by span over 180. So span is 1 meter. So 1 meter is 1,000 millimeter over 180. So this one is equal to 5.6 millimeter. And the induced deflection so this is 1 meter. Remember we said to calculate the induced deflection, we only used the imposed load, which is 270. So this is 270 kilonewton per meter. So don't use the GK, only use the imposed load when it comes to induced deflection. So the induced deflection is given by W L raised power 4 8 E I. So induced deflection is equal to W is 270 times length. So length is 1,000. You change 1 meter into millimeter. So this is 1,000 raised power 4. Then times 10 raised power negative 3. Because you are changing this kilonewton meter to kilonewton millimeter. So this meter we want it to be in millimeter so that it can be so that you can have a uniform unit with E. So over 8 times E, I said earlier, E for steel is always 205 kilonewton per millimeter. So E for steel is equal to 205 kilonewton per millimeter. So always remember this, always. And E is the Young's modulus of elasticity, yes, times I. Our I here is 87,400, then times 10 to power of 4. We change it from centimeter cubic to millimeter cubic. So 10 millimeter is equal to 1 centimeter. So therefore, is equal to 0.19 millimeter. So as you can see, 0.19 millimeter is less than 5.6 millimeter. Therefore, okay in deflection. And that marks the end of this question. So thank you for your time. And for those who have not subscribed to the channel, subscribe and hit the notification bell so that you may be the first person to be notified. We meet again in my next session.